Good to see you all here. Thank you for coming. It's my pleasure to welcome Professor Antonio Facchetti to Thayer today. So Antonio is a leader in my field and a number of other fields. He's a polymer chemist, organic chemist who's done some really interesting work in electronic materials that he's going to share with you today. And has really done now an extraordinary number of impactful works. A lot of papers that, if I look back 10 to 15 years, were important for me in graduate school, reading your work. So I appreciate having all that inspiration then and getting to see you here with us today. So today he's going to be sharing some advances in novel semiconductor materials and semiconductor devices, specifically flexible and stretchable electronic materials. And more recently, his work spans a number of other related domains: electrochemical gating of thin film semiconductors, and also neuromorphic devices, as well as metal halide perovskite materials for energy. So a lot of topics that I know my group and my students here are very interested in hearing about. And I'll also introduce Antonio's many qualifications. He's currently the Hightower Chair in Biopolymers at Georgia Tech, and he's simultaneously CTO and co-founder of Flextera. And so Flextera is a company that works in flexible electronics and has commercialized a number of your pioneering inventions. And he's also published over 600 research articles, more than 120 patents, and is a fellow of the Materials Research Society, as well as a member of the National Academy of Engineering and the National Academy of Inventors. So this combination of science and entrepreneurship is something we appreciate at Thayer. So we're all looking forward to hearing your talk today. So please join me in giving Antonio a warm welcome.
Thank you for the kind introduction. It's great to be here. It's a beautiful area. I've never been here, so I'm really thankful. And I learn new things talking to the faculty and students, so I really appreciate it. So I'm going to try to cover a few of the research you have done in the area of bioelectronics. My hope is to try to cover three areas. One is about unconventional semiconductor for different type of transistor architectures, particularly looking at organic for transistors which are called electrochemical transistors. And then I'm going to try to briefly talk about oxide semiconductor for thin film transistors. Then I'm going to report a couple of examples of try to make more mechanically ductile solar cell and photodetector using, again, organic material or perovskite. And if time allows, briefly going to talk about molecular doping of organics, which remains quite challenging, particularly for electron doping, N-type doping. So what my group has been interested now for a few years has been to develop materials, process, as well as prototyping for application in different areas, like flexible printed electronics, transparent electronic, different type of sensors, and energy harvesting and storage. So these are very different type of devices, and in many cases you need many different type of materials. But the sort of common denominator is to go from materials and devices which are usually brittle, hard, heavy, to materials and devices which are much more light, mechanically flexible, applicable to elastomer or plastic substrates. And if you look at this transition, just looking for making these devices, you need many materials, many different type of materials. But if you look at the transition in terms of the semiconductor, usually you think about going from inorganic type of material, which are very high performance, very scalable, durable, reliable, but usually they are very insoluble. They cannot process at low temperature, usually process at high temperature, hard and brittle, to material which are mostly organic. We do work also on oxide, and there are advantages there, and hybrid, which usually have lower performance. They are less stable, not too much chemically. Usually they are less stable to all the processing you have to do on top of the semiconductor in order to finish the device. But there are typically can be solution process, lower temperature, and the common thought is these are more soft and are more ductile, although this is a very gray area, as I know. So there's important question we try to answer. There is opportunity. One is question is, can some of these organics surpass or match the charge transport properties light to energy efficiency of inorganic semiconductors? They can retain these properties when we may implement them in mechanically flexible or stretchable devices. Can we achieve efficient ionic coupling with ionic signal or ultra small potential, which are biases, which are usually used in biology? Can we make inorganic semiconductor more ductile? Obviously, you can make a semiconductor, anything that can be made thin enough, it becomes flexible, right? But then can we actually do it in a different way, or can it be actually becoming mechanically stretchable? And for organic, can we find new way to dope the materials, which is challenging. Typically for inorganic is by elemental doping, and this you can really tune the charge transport, the material quite a lot. But for inorganic, organic, you cannot use simple element variation. You need to include a molecule. So for the transistor, there are many different types of transistors, and these are just 3 examples of transistors. They function quite differently, but a sort of the commonality about this different architecture, you see there are like 3 electrodes, what are called source, drain, and gate. You have a semiconductor layer, and in the semiconductor layer is where the red dots are the electronic carrier. This is where the electron or holes are moving into the material. And then, depending on the transistor, you can have an electronic insulator in all three cases. But in the thin film transistor, you use a dielectric material where you have a polarization. In this what are called electrical double-layer transistor, you have ions, but these ions, they are blocked at the interface. They don't penetrate through the semiconductor. Instead, in this electrochemical transistor, you have ions, and the ion penetrate through the bulk of the semiconductor and induces the carrier. And all of these, they have some advantage of disadvantages. The one I want to talk briefly today is about electrochemical transistors. So in this type of devices, basically you have, again, the source, drain, and the gate. You have an electrolyte with ion inside, and here you have the organic semiconductor. And if you apply a bias between these 2 electrodes, but there is no bias between the gate and the source, the semiconductor has no carrier. There is no electronic carrier. So it means if you apply a bias, but there is no carrier, in this current voltage plot, there is no current. So that you are in the off state of the device. If you apply a gate bias, what you do, there is a redox chemistry going on into the semiconductor. Ions get injected into the bulk of the semiconductor, and you have carriers, these electronic red dots. So you have carrier, you have a bias, you have a current. So you can turn on and off these devices by applying this secondary bias, and then you can control actually the on state, fine-tune the current by further changing this bias. Okay? So what is very important here? One very important here is that the semiconductor is get bulk, the carrier are induced throughout the bulk of the semiconductor. This is very different than in thin film transistor, when the carrier accumulation occurs only here. Here, the whole semiconductor gets filled of carriers. And the second thing is ions have to penetrate through the bulk of the material. So there is the dynamic of not only the electronic carrier moving, but also the dynamic of ions and going through the material itself, which controls what is the response of the device. And this is very important when you want to couple with biology and to try to simulate some biological functions. I'm going to show you in a second. So, what kind of semiconductor are used in this channel? These semiconductors are called mixed ionic electronic conductor, and are called mixed because you have both transport of electronic carrier and the ionic carrier through the material. These are usually solution processable, and most of the omics are also ductile because once they have a lot of mechanical flexibility in the chain, which really confer a much greater ductility compared to classical organic material, which are used in OLEDs or in solar cells. And this is an example of chemical structure of this material, which for those of you who are organic chemists, they might see here, these are called ethylene glycol chains, so you have a lot of oxygenated feature which helps the ionic injection through the bulk of the material. So these devices have, OECT has advantage because they can mimic some of the dynamic process of biology, because you can control how fast ions goes in and goes out depending on the chemistry and the type of ion and how fast you switch the bias. These devices operate at very low voltages. You see here, 0.5, 0.6 volt. Typical device like the transistor that I use in this backplane, they operate probably about 25, 30 volts. So this type of device usually needs very little power in order to switch. You can have a very large amplification because the carrier accumulates through the bulks, not only the interface, so larger amplification. And the process, all of this deposition are done at low temperature, though they are comparatively mechanically ductile substrates. So what are the challenge and the problem with OECT? There are several limitations. One is many electronic carrier are holes, positive carrier, but for organic N-type, so electron transported, they remain much more challenging. If you want to make complementary circuits, you need a P and N-type transistor. So if you want to make complementary circuits based on electrochemical transistor, you need a P and N-type. If you don't have a good N-type, you cannot make CMOS. And also, there is a problem with stability. When you turn on and off this device, you have a huge flux of ions going in the bulk and then coming out, going in, going out. So you can see what mechanically the semiconductor is stressed a lot because it's not simply an electronic transport. Another issue is fabricating this device. Usually this separation is only, very small, on the order of few microns, and this will require photolithography. And in terms of application, PEDO-PSS is the king. Most of the application in bioelectronics, also in type of circuitry type, that use OECT use this polymer, this semiconducting polymers. And so there is a state to invent new materials. So I don't want to talk too much about chemistry today, but I just want to give a couple of flavor what we have done and is important. So you have an OECT, you want to have ion going in and out, okay? So there's a few important questions that come up. So one is, if ion has to penetrate, can we use instead of a typical dense film, which is used typically in any semiconductor device, can we use instead of a porous film? Can we get better ion movement in and out? The second question is, are there different type of OECT architecture which can solve some of the processing issue? And the third one, can we create high-density OECT circuits? So here you have a liquid, so it's very difficult to have very large integration when you have a liquid as a dielectric, as electronic insulator. So to answer the first question, what we did is we took an organic semiconductor that we knew it works okay in a transistor, in an electrochemical transistor. And then what we did, we fabricated a film which has porosity. So this is the SEM of this film, which has been spin coated into a very high relative humidity atmosphere on the order of 95%. And what happens is, if you have a solution on top of your substrate and you spin it, the solvent evaporates very fast. When the solvent evaporates, it cools the substrate, right? Because you have the heat of evaporation. If your atmosphere has a lot of water, what happens is the water starts condensing, and these cavities is where water droplets form on the substrate, and the polymer is growing around of it. So this type of web has not been created using photolithography. It has been created simply by spin coating a film, a polymer film, under very high relative humidity atmosphere. So I can create this film, and then I can spin coat the same polymer in dry conditions, relative humidity used in a fab, 50%, 45% relative humidity, and you have a dense film. So we can make device based on the dense film and porous film of the same polymer. And what we see here, let me skip the fabrication, that these are the current or transconductance, it doesn't matter, transconductance, current, voltage responses, and this is for the dense, and this is for the dense film, and for the honeycomb, this porous film, the current is about 4 times larger, so it means we can accumulate more carrier per unit volume of the polymer. And the second important thing is you see here the separation between these 2 lines and these 2 lines. This reflects the dynamic of ion going in and out. If ion going in and out fast, the 2 curves should overlap perfectly. Instead, if they go in fast and they come out slow, they start not overlapping. And you see here they overlap much better because you have a web architecture in which ion can penetrate in and out much faster. So having this web type of morphology is good for organic material, for OECD. And we have done it also for other polymers. Another advantage of this web architecture is these are the dense, this is the honeycomb film. And here we transfer the film on an elastomer, we start stretching. And here I stretch in this direction. And for the dense film, these start cracking about 60% strain. Instead of for the honeycomb, you start cracking it about 110, 120. Basically, this honeycomb morphology, which has been used widely, for example, in aerospace technologies and to enhance ductility, to enhance dissipation, energy, mechanical dissipation mechanism, applies also to this organic. So better ion intercalation and better ductility for the same polymer when you use this honeycomb. So we can make these devices which can stretch it and the current is stable and blah, blah. What is interesting is for this type of devices, the limitation, you start getting failure not because the semiconductor is cracking, but because the electrical contacts start cracking. So if you have some clever way to integrate this honeycomb with contacts which are much more ductile, this would make an impact. And it's not easy. I've been trying to do it. It's very difficult. So if you have some idea, please let me know. I can give you the honeycomb film. And then we can do some integrate, we can do some physiological sensors. These are well done. There's nothing new here. What's quite new is that we can get the same signal when you stretch the platform. This is what was the real novelty of this part of the work. So I said that one of the difficulty in many of these OECTs is to integrate them and achieve high integration. So the way to enhance integration is to stack in one device on top of each other, right? So can we do this using for OECT? So can we actually have the 2 contacts being one on top of each other and compare with the conventional device which is planar? So the question is, can this device work? But what is the issue? The issue is that in order to have the ion to go in, you have to have a real estate, right? You have to have surface. So the surface in a planar device, which is widely used, is micrometers scale. Okay? But if you make a device where the 2 electrodes are stacked on top of each other, the area, the window in which the ion can go in is given by the thickness of the semiconductor. The thickness of semiconductor is 60, 70, 100 nanometer. So here, it's not obvious that ion can go in and go out efficiently. But if it works, it would be advantageous. So we work, okay, I somehow, I forgot about it, I put down the question. So the question is, can we actually get injection of ion in and out from these nanoscopic interfaces? And the other question is, can this device be stable? If ion assume they go in, they also water or the solvation of the ion is going to go in. If this goes in, then it means the device has to expand. If it expands and then it contracts because you turn the device on and off, then the gold electrode on top can start being peeled off, so it can be delaminated. So that is also another question which was open. And then if this works, can we actually stacking this up to make more integration? So we made devices which are, this is called lateral, and this is the vertical architecture, which is simply basically an array of crossbar of gold, in which in between you sandwich the same semiconductor, here this light green. And this shows how the device is made. We just deposit by thermal evaporation a gold line, we deposit the semiconductor, a second gold line, and we put the electrolyte on top. And this is the cross-section SEM of this device here, which shows the window in which the ions have to penetrate. Here the thickness you see is on the order of 80 nanometer. So very small window. This is the top gold, and this one is the bottom gold. And to demonstrate the concept, we use two organic semiconductors. This is a P-type semiconductor to transport positive carrier. This is an N-type semiconductor to transport negative carriers. And this device also works quite well. It was not obvious when we started working, but if you take, for example, so these are a device for the vertical, and this is the control device with the conventional. This is for a P-type semiconductor. This is the current. If you compare with this current, you see the current is much larger amplification. For the N-type, this is the current, and this is the current for the conventional device, much larger. So it works very, very well. Also, it works well in terms of stability. We can cycle this device many, many times. We still don't understand why this is the case. And we actually, right now we are doing AFM experiment where we put the cantilever of the AFM and we monitor for different type of ions and semiconductor how is the expansion of the channel when the ion goes in, when you're operating the device. For some semiconductor, actually, you see that after 20, 30, up and down, you see the gold like delaminating. For some other, it's much more stable. But we still don't understand why this is the case. We can make this stable because there is a trick that I don't have time to talk about. You can read the paper. It's not a trick that is hidden. It's a trick that is explained. What is also good about this array that you can really start doing something that is done on display. In display, in order to control to create the image, you need to switch the bias of each pixel using what is called driving circuits, which control the biases. So we can do the same thing with OECT because we can basically with crossbar we can fabricate one OECT, and also we have demonstrated we can put 2, 3, 4 OECT, one on top of each other, and this can be done also on a wafer scale. So now we know that we can use these vertical devices, and they really respond quite well. One of the things we are very interested in, and actually the community is interested, is try to create a platform where you go from sensing to processing information or transducing information and to memory or learning. And our goal is to do this transition using only OECT, electrochemical transistors. And the core to do that, and we started working on that. We haven't achieved completely we are still far away in the memory, and we are still a little far away on the sensing part. But in this work, basically what we do, we use conventional mechanical sensors to input current into this core. And this core is what Simone Fabiano from Linköping, who invented the architecture, we applied that architecture using our VOCT, is what is called an organic electrochemical neuron. Why it is called a neuron? Because if you can fabricate a core of this type, basically you can transduce an input current into a potential which oscillates. And this is called action potential or spike. So it mimics what neurons do. So in order to do that, we have to be able to create this unit. And in this unit, I don't remember if I put the image. No, I didn't. What is key in this unit are 1, 2, 3, 4, 5 transistors, 5 electrochemical transistors. 2 of them here are N-type, so these transport electrons. These 2 are P-type, and this one can be either P-type or N-type. In this work, we did P-type, but it doesn't really matter. But you need basically two blocks, and each of these blocks is called an inverter, okay, which needs an N and a P-type. If you can create this block, then you could, in theory, achieve this conversion of this current, or sensing of the current, or transduction of the current, into an action potential. So in order to create this block, you need to have an N and a P-type transistor, but also what is very, very important is that the 2 transistors have to be a sort of symmetric in terms of performance. It means both the turn on of the transistor, which is given by this point and this point, and the current they achieve have to be very comparable. So you can do this by changing the dimension of the one transistor. You make it bigger, one other transistor you make it smaller, one you make it thicker, one you make it less thick. But this will complicate the fabrication, right? So ideally, you would like to make these 2 transistors, and they using 2 material, and they work symmetrically. And this is what we have been able to do by chemistry. We made these 2 polymers, and these 2 polymers in this vertical architecture these very symmetric IV characteristics. This means that we can make an inverter which has a very nice inversion and very nice gain. And then based on this, we can build our neuron. This is just simply highlighting what I just said. And here is that, so the input current, which is given by the sensor, it doesn't matter. You see here it varies from about 100 microamperes down to 100 nanoamps, and you see here that the frequency at which the voltage oscillates changes. So we can really correlate the current to this voltage. And by changing also the capacitance of these 2 capacitors, we can tune it further. So basically, using this electrochemical neuron, we can tune the spike in frequency from about roughly 0.1 or something like, 0.1 to about 140 hertz, which spans many type of neurons, spiking neurons activities. Okay, now let me cover briefly another topic, metal oxide. So we are mostly interested in organic, but we've done quite some work on inorganic, particularly oxide. And we like oxide because these materials are optically transparent, and also they have for many organic and also for silicon, in order to get good transport, charge transport, you need to have a crystalline phase, right? They have to be crystalline. But oxide, also in the amorphous state, they have a very large electrical carrier mobility, so electrical conductivity, depending on the carrier density. Also, the other great advantage is that this material can be processed in ambient. You can process in ambient silicon, right? You start from a silane, and you spin coat it, but not in front of you, otherwise it's going to catch fire, you're going to burn, right? So you can spin coat silicon in a glove box, but the quality is usually very bad. But for metal oxide, you can do it in ambient. What is the question we wanted to ask is, we can process in ambient, but usually after deposition you need to anneal the precursor of the metal oxide at high temperature. So the question is, can we reduce this process in temperature? And another question we ask, since I'm an organic chemist, is can you actually use polymers, organic polymers, to be included into the formulation of the oxide in order to tune the morphology or the charge transport of the corresponding product or the corresponding metal oxide film? So what is the typical way to prepare a salt oxide? There's many ways, and we know well us quite a lot on that. When we started this project back, I think it was 2008, something like that. The most classical way to do it is, for example, you want to make an oxide which is indium oxide. So you have indium as a metal. So you start from, I don't know, indium chloride or indium nitrate. In a solid, you dissolve it, you put it, throw in, sometimes you put in a little base, and you can put a little ammonia or whatever, and you spin coat, and then usually you get a dry film, which is a big mess, and then you anneal, you burn off everything, and 400 and 700 degrees, you get the indium oxide. So this is the classical way to do it. But here, you cannot do this on plastic. The budget is too high. So how can we go around? The way to do, we did it going around is just to keep the same composition, but then we throw in a redox pair. So this is an oxidizer and the fuel, and the idea is when we get to this mass has a lot of internal energy, and just giving a little bit of input, this redox pair start reacting in the solid state, generating a lot of heat, and this heat is used to burn off whatever the reagents, which gives the oxide. And we have done this, oops, the video is not working. That's okay. No, I cannot make it work, but you need to trust me. Here there is the video where we have this film, and we put it at about 200 degrees, nothing happened. And if you take this film at 200 degrees, you start see a lot of smoke coming out because it reacts and it forms the oxide. So this is called combustion synthesis, which has been used for bulk material, but has never been used for film. And what was quite interesting, so based on this oxide film, we made transistors. These are thin film transistors. So here the carrier accumulation is only in this area, but it doesn't matter. What this graph is telling you is that the performance of the transistor correlate with the heat that this redox pair is producing. So basically you can select for the same composition a different redox pair, and you can get different performance based on the heat generated. So it's a chemical way to control the formation of the product. One of the drawbacks of this technique is that we generate so much heat that usually we can also crystallize IGZO. So if you make the film thick enough, IGZO crystallizes. One of the things we have been interested in is to make some of this oxide at least mechanically bendable. And the typical way to make oxide film more tolerable to deformation is to make them amorphous. Okay, IGZO is much better than indium oxide, for example. And why? Why? Because you take your metric and you start throwing in a lot of elements, and then this creates disorder, you depress the crystallization temperature. We wanted to do it in a different way. And the way we did it is basically keeping the same formulation I just talked to you about before, and then we throw in a polymer inside. And then when you do the conversion chemistry, depending on the temperature, some of the polymer chain remain embedded into the polymer in the oxide matrix. You can actually choose, depending on if you want more or less polymer, you can change the chemistry of the polymer, but the concept is you end up with a film which has some residue as memory of the polymer you are using. And having a polymer in there, what does is enhance the crystallization temperature. You get amorphous phases, also when using combustion. And also what you can do, you start making film which are more tolerable to deformation. For example, this is the performance of indium oxide. These are the initial performance if you don't use any polymer. If you use a little bit of polymer, you sacrifice the initial performance, but then the performance remains much more stable when you start bending the substrate. So that was one way to enhance ductility. Another way we did it is basically to spraying. So we use a sort of polymer to somehow absorb your salt, your indium oxide precursor, for example. And what you do, you spray the formulation instead of spin coating the formulation. And what you end up is you start getting fibers. And I think I have a picture, yes. So these are silicon wafer, and this is on purpose. I asked the student to take the silicon wafer, separate them, so you see. And you see that you get this fiber. This fiber is not the oxide. These fiber are the polymer, which absorb the precursor of the oxide. How do I go from this to the oxide? Is by burning off everything. We take this fiber, we burn them off, and then we get oxide fiber, which has the composition of the salt I've been using. And in this way, we made a number we can do this process. Of course, we cannot do it directly on a plastic or elastic substrate. We typically do the conversion of the fiber precursor into the fiber oxide on a silicon substrate, and then we transfer them to an elastomer, and then we can make TFT, we can make a resistor, and we made a number of sensors and things like that. That's an example of a strain sensor, pressure sensor. We did a few. And another fun things we have done is that we can actually mix and match the transistor. For example, for those of you who are familiar with organic material, organic semiconductor usually they transport well positive carrier, but they transport much less negative carrier. Instead of oxide is exactly the opposite. Oxide can transport well negative carrier electrons, but much less holes. So what we did in this work, we made an inverter, so where you need a P and N type, where the P is an organic, functioning as an electrochemical transistor, and the N type is an oxide, which is here should be a negative, where it works as an electrolyte, electrical double layer transistor. So we can match basically the two and make different type of inverters, and these have been used for some electrophysiology, very simple, basically amplifying the voltage that you can measure around the eye from sub-millivolts to these tens of hundreds of millivolts. So you can mix and match these transistors. All right, let's see if I'm doing good with time. I think I can talk about this. So another area we have been interested in are solar cells, and we have a program with the Navy to try to make solar cell more stretchable. They want to basically we have specification where we have to have a module which has a certain size and has to be attached on a lifeboat which inflates to a certain level, and upon inflation, the solar cell should function in the same way. So it doesn't have to be extremely stretchable, but at least has survived this fast expansion process. So there's many different types of solar cell. The one we are mostly interested in are bulk heterojunction organic solar cell. So solar cell concept is simple, right? You shine light on something, on the device, and you convert whatever the solar energy into electrical energy. In the bulk heterojunction organic solar cell, the photoactive layer has two components because the exciton cannot be split like in silicon or in other inorganics. It has a red phase, which is called donor, and a blue phase, which is called the acceptor. So it means basically you shine light on your photoactive layer, you form an exciton, which is an electron-hole pair. This pair migrate to the interface between the donor and the acceptor phase. The holes move in the donor phase, which is the p-type semiconductor, and the electron moves in the N phase, the acceptor phase, which is the N-type semiconductor, and you have conversion of light into carrier. Okay, and there's been amazing progress in this area in the past about 5 years. So right now, certified efficiency are more than 21%, when only 10 years ago we were still struggling on the order of 10%. And this has really been due to the developing of new N-type acceptor, which are now, this is called Y6. This molecule is a good electron transporting material in bulk heterojunction solar cell. What is the problem is that blends, if you take any of this acceptor, any of this donor polymer, no matter if the donor polymer is ductile or not. As soon as you take an acceptor and you put it into the donor, you embrittle the blend dramatically. So this becomes very brittle blend. Also, if you start from a polymer donor, which is quite, for example, stretchable. So can we try to find new way to make some of this cell ductile? So one way we did it is actually making it as an acceptor, not a small molecule, but making itself a polymer, and then using as a polymer, for those of you who are organic chemists, they might see easily. For those of you who are not, it might be more difficult. So in this acceptor, which we call 1, it has a double bond. In this second acceptor, which is 2, it has a single bond. In organic chemistry, a single bond is much more fluffy, has much freedom to move around compared to a double bond. So the question is, if we start, basically plasticizing certain area of the acceptor, am I going to get better ductile cells? And the answer is actually yes. So if you take the blend of this donor with the molecular acceptor, this starts cracking about 5%. If you use the acceptor 1, it starts cracking about 10% strain. And then if you use the acceptor 2, you are between 12.5% and 15%. So you really start getting this blend which are more stretchable. And then we can make, based on that, I don't know if the video is going to work, we can start making cell where you start stretching and releasing the strain, and they are much more stable compared to the control. This is a little, there is a little trick here because you start from a pre-strained substrate, so you're not applying a huge strain. The actual strain here that are applied are in the order of 9%. But there's considerable difference between what we call the acceptor number 2 with the single bond compared to the one of double bond and compared to the molecular system. So we can start embedding ductility. Another way we did it is actually by changing the structure to a certain extent of the molecular material. So in this work, basically what we did is we take the same donor that I showed you before, the red phase, and then as acceptor we can use the classical acceptor which embrittle the blend, or we can use the second acceptor. For those of you who are organic chemists, the major difference between these two systems, they say, well, there is no difference. As a matter of fact, there is a big difference in the chain where you have this trialkyl-silyl substituent. And this makes actually a huge difference. What kind of difference is making? Also, we tested 2 different donors because this is known to be a more brittle donor polymer. This is more ductile polymer. So we have a possibility to test our hypothesis that this material works well, testing a few different combinations. So first of all, the first question is, we know that these 2 cells based on these 2, this couple, this donor and acceptor pair, gives an efficiency of about 16%. This is well known, but they are very brittle. The question is, how does the efficiency between this one, which should be the most ductile, going to be? And as a matter of fact, these new blends have very similar efficiency to the control, so which is good for when you are making a comparison. The other thing we did is these are images of film which has been strained at different extent. So this is the classical donor, which is PM6. This started cracking at about 26%. The different donor, the donor number 2, is much more ductile, which is on the order of 70%. Then we can do also strain of the pure acceptor phases. And you see that both material are very brittle. Okay, so the new material is actually not a better a stretchable film. It doesn't give any better stretchable film compared to the conventional acceptor. But what is very, very different is when I start blending them. And in this video, I don't know if it's going to work. This is the control device. This cracks on the order of 5%. So the pure PM6, it cracks about 26%, but when you throw in this acceptor, the blend becomes more brittle. This is expected. And if you look at this video, we start stretching, and it cracks right away, about 5%. This is the new blend, using this new, the new donor and the new acceptor. And this is start stretching, you keep stretching, and you go to about 90%. So you see here there is a very big difference. When you add this one here, you are not embrittling the polymer. You actually enhance the elasticity. So all of these acceptors act as an anti-plasticizer, instead of this acceptor act as a plasticizer. So fundamentally is different. And this is due to a different things that we study that I don't have time to discuss it, but basically you have to believe me, this is mostly due to the miscibility and the fact that this enhanced miscibility in the donor phase reduces the energy for the beta relaxation of the polymer backbone, something that other acceptor cannot do. And so we made cell, and as expected, the one based on the new blend is you can stretch it. It retains the performance much more compared to the comparison. That's somehow expected. Another thing that I'm not an expert in perovskite at all, so I think I published 5 papers, and I have to thank all the collaborators. But these materials, as you know now, they're widely applicability. One of the problems with this perovskite film that they are very, very brittle. You have a lot of grain boundaries, and there it is where the failing mechanism occurs. So if you want to make some of these inorganic, well, it's organic, inorganic, they are more hybrid, depending which kind of ions you are using. If you want to make this material more ductile, how can we do that? And the way we started doing it is basically learning from our work we've done on an electrochemical transistor. So basically what we did here, we took a plastic polymer. This is not a semiconducting polymer. This is just a plastic polymer. And this polymer has been spin-coated in a very high relative humidity. When you do that, you create this honeycomb, these holes into the polymer film. Then what we did is, inside these holes, this grid is basically this hole cut from the side. These are SEM image of the polymer. We're using the 2-step process. We first fill the hole with lead iodide, and then using the ion you want to use, the metal halide you want to use, organic halide you want to use, you create your perovskite composition. And what you see here, what is quite neat, the perovskite like to grow in only in the holes of the polymer. So you're basically creating a matrix in which the holes are filled by the perovskite. And when you do that, and you do the process on parilene, you can really make films where you can make perovskite films which are very, very, they don't crack. If you can deposit perovskite on parilene, but then when you start, the parilene film is very thin, and it starts bending, you form a lot of cracks. When you use this pixelation of the perovskite, this crack does not occur, and so we can, in this particular case, we made photodetector, and we have factor detector which are much more stable when you strain them. You can strain up to 100%, or about different strain, compressing a strain cycle. So this is a way to make some of this inorganic more stretchable. How much time do I have? Because I can stop here.
True. This might be a good point, though.
Okay, very quickly. Doping. So obviously, as you know well, for silicon or inorganic, the way to dope is to throwing in elements. For organic, what is done, this is an example of an organic semiconductor, pentacene. You can introduce electron by using, for example, this ruthenium complex, or you can extract electron to make it p-type by using this fluorinated molecule. The major issue for organic is that this process is usually easy. You can easily p-dope organic, but the electron dope is much more difficult. And usually does not occur by having a molecule which transfers the electron directly. Usually you use what is called a precursor dopant. So it means you use a molecule which itself does not have the energy to transfer the electron. But what you do some chemistry at this molecule to convert to a species which then they can donate the electron. So this process is energetically demanding. So it means you have a problem of the doping itself, but you have solved the problem to convert the precursor of the dopant into the active species of the dopant which transfer the electron. So since this process is difficult, one question we ask ourselves is, can we use a catalyst which helps this chemistry? And it's something that works well. We use many different types of systems. Let me just, as a catalyst, for example, we use gold. Let me just show you the video, which itself should tell you a lot of things. So basically, these are a mixture of a molecule I want to dope. I want to transfer the electron. This is the dopant. And here I have the mixture of the two on a glass slide. Here is a room temperature. Usually, to have this chemistry, you need to anneal the film at 180 degrees for several hours. If you do it with a little catalyst, you see they change the color. Change the color means the reaction happens. So the reaction happens instantaneously. Okay? So it's really, using catalysis, it's really a way to enhance this doping ability of organic molecules. This is bad, but also this is bad. This is too slow. This is something you cannot control because you cannot create formulations which are stable enough to do the chemistry. So this is the last thing I'm going to tell you. The one we did it is basically to protect the catalyst, and this is gold particle, with a shell which decomposes at a low temperature, about 60, 70 degrees. So we can include the catalyst into the mixture, and then only when you heat the film at a temperature, not at room temperature, but about 60, 70 degrees, you can have the chemistry going on. And let me skip this. It's just reiterating with numbers. And here there is a video. So the video I cannot show. So let me conclude. So I show you examples where we use this OMIAC, where we can make them more ductile using this honeycomb semiconductor architecture. We can make these vertical devices, which works quite well. We can use these vertical devices to make this organic electrochemical neuron. We are far away to what we want. The key challenge now is really to find a mechanism to transduce the action potential into a current that then can be stored very reliably. This is what remains now the key aspect of that work. Then I told you a little bit about the oxide, a couple of strategies to make them more ductile. I talked about solar cell. We can plasticize the organic in a couple of ways, or we can plasticize inorganic using this matrix. And finally, this work with catalysis. I acknowledge all the students. I think I put picture of them. They did all the work. And these are some of the collaborators at Georgia Tech. Mostly now, this is mostly work on the solar cell. For the oxide, they work on collaboration with Tobin Marks and others at Northwestern. A lot of work with the dopant was done at my company and in collaboration with Fabiano. And where is, no, I cannot have, I forgot one person, which is very important. He will kill me. No, here he is. So Zhugang Guo in Shenzhen. He actually, I have to give complete credit, he invented the catalytic process. I helped with some important experiment, but I have to give complete credit to him. He invented it. And finally, for the perovskite pixelation, now I'm working with Georgia Tech with the group of Correa Buena. And these are some of the funding agency, and thank you for